Picture this. Our universe wasn't born from a singular fiery explosion. Instead, it was forged in the aftermath of a collision between two colossal cosmic planes floating in a higher dimensional space. What if the story of creation isn't about a beginning, but an eternal cycle of destruction and rebirth? Welcome to the Ekpyrotic Universe, where mysteries of the cosmos defy the Big Bang theory and take us to the very edges of scientific understanding. Stay with us as we delve into this revolutionary concept that challenges everything we think we know. The Ekpyrotic Universe theory is as enigmatic as its name, which derives from the Greek word ekpyrosis, meaning conflagration or cosmic fire. This concept originated from ancient Stoic philosophy, which envisioned a cyclical cosmos undergoing periodic destruction and rebirth. Modern theoretical physicists breathed new life into this idea in the early 2000s, introducing it as an alternative to the widely accepted Big Bang theory. Unlike the Big Bang, which suggests the universe emerged from a singularity, an infinitely dense point where all matter and energy were compressed, the Ekpyrotic Universe posits that our cosmos arose from the collision of two massive parallel branes. These branes, which exist in higher dimensional space, interact in a way that creates the conditions necessary for the birth of a universe. Imagine a three-dimensional sheet floating in a vast, unseen ocean of dimensions. Now imagine another sheet, parallel to the first, drifting closer over the course of billions of years. When these sheets, or branes, collide, the energy released transforms into the matter, radiation and structures we observe in the universe today. This collision eliminates the problematic singularity, offering a smoother and arguably more elegant explanation for the birth of the cosmos. But why would these branes collide in the first place? The answer lies in the mysterious forces that govern higher dimensional space. In this framework, the branes are not static. They oscillate and vibrate in ways that are almost impossible to visualize. Over time, gravitational forces pull them together, setting the stage for a cosmic event that reshapes reality itself. The Ekpyrotic model isn't just a theory of beginnings, it's a theory of cycles. After the collision, the branes recoil and begin drifting apart once more, only to repeat the process billions or even trillions of years later. This cyclical nature raises profound questions about the nature of time, space, and existence. Could it be that our universe has been reborn countless times before and will be reborn countless times again? To understand the Ekpyrotic universe, we must first dive into the realm of string theory and M-theory, the mathematical frameworks that form the foundation of this idea. In string theory, the basic building blocks of the universe are not particles, but tiny vibrating strings of energy. These strings can stretch and oscillate in multiple dimensions, creating the fundamental forces and particles we observe. M-theory, an extension of string theory, introduces the concept of branes. A brane, short for membrane, is a multidimensional object that can exist in a variety of forms. Our universe, according to M-theory, is a three-dimensional brane embedded in a higher dimensional space. But it's not alone. There are other branes, potentially parallel to ours, floating in this multidimensional arena. When two branes come into contact, their collision generates an immense amount of energy. This energy doesn't just sit idly. It transforms into the hot, dense plasma that forms the basis of a new universe. In the Ekpyrotic model, this process replaces the singularity of the Big Bang, sidestepping one of the most puzzling issues in modern cosmology. What's truly fascinating is the predictability of this cycle. The separation and collision of branes follow a pattern, suggesting that the universe undergoes periodic renewal. This notion challenges our traditional understanding of time. Instead of a linear timeline stretching from a singular beginning to an eventual end, the Ekpyrotic model envisions time as a loop, with no true start or finish. Scientists have proposed several ways to test the Ekpyrotic model, including studying the cosmic microwave background radiation, CMB. This faint glow, a remnant of the early universe, carries imprints of its origins. While the Big Bang model predicts a uniform pattern of CMB fluctuations, the Ekpyrotic model suggests subtle differences that could confirm the existence of colliding branes. But here's the twist. Higher dimensional physics is notoriously difficult to test. Much of the evidence for the Ekpyrotic universe lies in mathematical models that stretch the limits of human comprehension. Yet, if proven true, this theory could revolutionize our understanding of the cosmos and our place within it. One of the most compelling aspects of the Ekpyrotic universe is its ability to address some of the lingering mysteries in cosmology, problems that the Big Bang model struggles to resolve fully. Among these are the flatness problem, the horizon problem, and the mystery of dark energy. The universe appears to be remarkably flat, meaning its geometry is neither curved inward, like a sphere, nor outward, like a saddle. In the context of the Big Bang theory, achieving such flatness requires a delicate balance of conditions during the universe's earliest moments. This is often explained by the theory of cosmic inflation, which suggests the universe underwent an unimaginably rapid expansion immediately after the Big Bang. The Ekpyrotic model offers an alternative explanation. During the slow approach of the branes before their collision, the universe naturally flattens out. This gradual process eliminates the need for the extreme fine-tuning required by inflationary models, providing a more elegant solution to the flatness problem. Another mystery is why the universe is so uniform. No matter where we look, the temperature of the cosmic microwave background radiation is nearly identical. In the Big Bang model, regions of the universe would have been too far apart to exchange information or energy fast enough to equalize temperatures. This problem is also resolved by inflation, but the Ekpyrotic model explains it differently. In the Ekpyrotic framework, the slow contraction of the branes allows for the uniform distribution of energy across the universe before the collision. This ensures that the cosmos begins in a homogeneous state, naturally leading to the observed uniformity in the CMB. Perhaps the most profound mystery in cosmology is the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. While the Big Bang theory leaves this phenomenon largely unexplained, the Ekpyrotic model suggests a link between dark energy and the separation of branes. After the branes collide, they recoil and begin drifting apart. This separation creates a tension in the fabric of space, manifesting as the effects of dark energy. In this view, the accelerated expansion of the universe is not a random anomaly, but a predictable consequence of the brane dynamics. By addressing these cosmic puzzles in a unified framework, the Ekpyrotic universe offers a tantalizing glimpse into the workings of reality itself. But the theory doesn't stop here. It raises even deeper questions about time, existence, and the multiverse. If the Ekpyrotic universe operates in cycles, what happens during the transition from one universe to the next? This is one of the most mysterious aspects of the theory and a topic of intense debate among physicists. In the moments before a brane collision, the universe undergoes a phase of slow contraction. During this phase, the distances between galaxies shrink, and the energy density of the cosmos increases. This contraction sets the stage for the creation of new matter and radiation during the collision itself. But what happens to the old universe? Does its information vanish entirely, or is it somehow imprinted on the new cosmos? Some scientists speculate that the laws of physics could evolve slightly with each cycle, leading to universes that are similar but not identical. This raises profound questions about the nature of memory and continuity in the cosmos. Furthermore, the Ekpyrotic model suggests that the end of one universe is not a destructive annihilation, but a transformative rebirth. The process of contraction, collision, and expansion creates a seamless transition between cycles, ensuring that the universe remains eternal. In this sense, the Ekpyrotic universe is not just a scientific theory, but a philosophical framework that challenges our deepest assumptions about time and existence. If true, it means that the cosmos has no ultimate beginning or end, only an infinite series of chapters in an endless story. While the Ekpyrotic model is a fascinating alternative to the Big Bang, it faces significant observational challenges. Testing its predictions and distinguishing them from those of inflationary models require advanced technologies and innovative methodologies. One of the key predictions of the Ekpyrotic model is a unique pattern in the cosmic microwave background radiation, the faint afterglow of the early universe. In the Big Bang model, cosmic inflation generates a uniform pattern of CMB fluctuations with a mix of scalar, vector, and tensor modes. The Ekpyrotic model, however, predicts a suppression of tensor modes, gravitational waves generated during the contraction phase. Detecting these differences is incredibly challenging. Current experiments like the Planck satellite and the upcoming CMB-S4 observatory are designed to measure the CMB with unparalleled precision. If these instruments fail to detect the tensor modes predicted by inflation, it could bolster the case for the Ekpyrotic universe. However, the absence of these modes alone is not definitive proof, as alternative inflation models could also produce similar results. Another challenge lies in observing the higher dimensional branes central to the Ekpyrotic model. These branes exist in a realm beyond our three-dimensional perception, making them inherently difficult to detect. Advances in high-energy physics, such as experiments at the Large Hadron Collider, may provide indirect evidence by probing the existence of extra dimensions or the nature of gravity at small scales. Moreover, scientists are exploring the possibility of gravitational waves from the Brane collision itself. These primordial waves, if detected, would offer a direct window into the ekpyrotic process. Instruments like LIGO and Virgo are pushing the boundaries of gravitational wave astronomy, but capturing signals from the early universe remains a daunting task. The distribution of galaxies and cosmic voids across the universe also holds clues about its origins. The Ekpyrotic model predicts subtle differences in the large-scale structure of the cosmos compared to inflationary models. Mapping these structures with next-generation surveys, such as the Euclid satellite and the Vera C. Rubin Observatory, could help distinguish between the two theories. Despite these challenges, the pursuit of observational evidence for the Ekpyrotic universe is driving innovation in both theoretical and experimental physics. The quest to uncover the truth about our cosmic origins is not just a scientific endeavor, but a profound exploration of what it means to exist. One of the most intriguing aspects of the Ekpyrotic universe is its connection to the multiverse, a concept suggesting that our universe is just one of many coexisting realities. In the framework of M-theory, the existence of multiple branes implies the possibility of countless other universes, each with its own unique properties and physical laws. If branes are floating in higher dimensional space, it's conceivable that our universe's brane is not the only one. Other branes could exist nearby, interacting in ways that create entirely separate universes. These parallel universes may differ in their fundamental constants, the types of particles they contain, or even the number of dimensions they encompass. In this view, the multiverse is not a distant abstraction, but a direct consequence of brane dynamics. Every collision between branes could give rise to a new universe, creating a vast interconnected web of realities. Our own cosmos could be just one node in this infinite network shaped by the unique conditions of its brane collision. The cyclic nature of the Ekpyrotic model raises fascinating questions about the multiverse's temporal structure. Are all branes following similar cycles of collision and rebirth, or do they evolve independently? If universes are continuously created and destroyed, what happens to the information and energy of the previous cycles? Some physicists propose that the multiverse could function like an enormous cosmic ecosystem, with branes interacting in ways that preserve the overall energy balance of the higher dimensional space. This idea challenges traditional notions of entropy and thermodynamics, suggesting that the multiverse operates under laws we have yet to discover. The multiverse theory also raises profound philosophical questions. If countless universes exist, what makes ours special? Is the existence of life an extraordinary coincidence, or is it an inevitable outcome in a multiverse filled with infinite possibilities? The Ekpyrotic model, with its emphasis on cycles and rebirth, offers a unique perspective on these questions. Rather than viewing our universe as a singular event, it frames existence as a continuous process of renewal, where every collision creates the potential for new forms of life, matter, and structure. This perspective invites us to rethink our place in the cosmos and consider the possibility that we are part of an infinite, ever-evolving tapestry of realities. The Ekpyrotic model and the Big Bang theory represent two competing narratives about the origin of our universe. While both explain key features of the cosmos, they differ fundamentally in their assumptions, mechanisms, and implications. Let's delve into a cosmic showdown that pits these two theories against each other. Initial conditions, a singular beginning, or eternal cycles. The Big Bang theory posits that the universe began as a singularity, an infinitely dense point where space, time, and matter emerged in a cataclysmic explosion. This singularity is often seen as the ultimate beginning of everything, though its precise nature remains a mystery. In contrast, the Ekpyrotic model rejects the need for a singular beginning. Instead, it describes an eternal cycle of brane collisions, each giving rise to a new universe. This framework eliminates the need for a singularity, offering a more continuous and potentially infinite narrative for cosmic evolution. The role of inflation. A cornerstone of the Big Bang model is the theory of cosmic inflation, which explains the rapid expansion of the universe immediately after its inception. Inflation solves several cosmological puzzles, such as the flatness and horizon problems, but it introduces its own set of challenges. For example, inflation requires a finely tuned energy field, and its mechanisms remain speculative. The Ekpyrotic model sidesteps inflation entirely. Instead, it attributes the universe's large-scale structure and flatness to the gradual approach and collision of branes. This eliminates the need for an inflationary phase, simplifying the narrative while providing alternative explanations for observed phenomena. Observable predictions. Both theories make predictions about the cosmic microwave background, but they differ in subtle ways. Inflation predicts a significant presence of tensor modes, primordial gravitational waves, while the Ekpyrotic model predicts their suppression. Future observations of the cosmic microwave background could help distinguish between these theories, potentially reshaping our understanding of cosmic origins. Implications for the multiverse. The Big Bang theory doesn't inherently require a multiverse, though some inflationary models suggest that inflation could produce multiple bubble universes. The Ekpyrotic model, on the other hand, is deeply tied to the multiverse concept. The existence of multiple branes naturally implies the possibility of countless other universes, each created by its own brane collision. By challenging the assumptions of the Big Bang and offering an alternative narrative, the Ekpyrotic model invites us to reconsider everything we thought we knew about the cosmos. Time is one of the most mysterious aspects of the universe, and the Ekpyrotic model offers a radically different perspective on its nature. In the traditional Big Bang framework, time begins at the moment of the singularity. There is no before the Big Bang, as time itself is a product of the universe's expansion. This idea, while mathematically consistent, leaves many philosophical questions unanswered. The Ekpyrotic model introduces the concept of cyclic time, where the universe undergoes endless cycles of contraction, collision, and expansion. In this view, time doesn't have a single starting point, but is a continuous loop without beginning or end. This perspective aligns with certain ancient philosophical traditions, such as Hindu cosmology, which also describes time as cyclical. Cyclic time challenges our linear understanding of causality. If the universe is eternal, what caused the first cycle? And if time itself is a product of brane dynamics, does it exist independently of the universe? These questions push the boundaries of both science and philosophy, inviting us to rethink the very fabric of reality. One of the key challenges of cyclic models is entropy. In thermodynamics, entropy, or disorder, tends to increase over time, suggesting that a cyclic universe should eventually run out of steam. The Ekpyrotic model addresses this by proposing that entropy is reset during the brane collision. This mechanism ensures that each new cycle begins with low entropy, preserving the arrow of time. By reimagining time as an eternal cycle, the Ekpyrotic model offers a profound and potentially unsettling vision of the cosmos. If time is infinite, what does that mean for our place in the universe? Beyond its scientific merits, the Ekpyrotic universe raises profound philosophical questions about existence, meaning, and the nature of reality. Human beings are wired to think in terms of beginnings and endings. We are born, we live, and we die. Our understanding of time and existence is deeply rooted in this linear perspective. But what if the universe operates on entirely different principles? The Ekpyrotic model suggests that beginnings and endings are illusions, mere phases in an eternal cycle. This idea challenges our sense of individuality and permanence. If the universe is eternal, what significance does a single human life hold? Are we fleeting moments in an endless cosmic dance, or is there a deeper purpose to our existence? If the universe operates in cycles, does that mean history repeats itself? Are we living in a loop where every action and decision is predetermined? While the Ekpyrotic model doesn't explicitly address free will, its implications for determinism are profound. Some interpretations suggest that each cycle is slightly different, influenced by quantum fluctuations or variations in brane dynamics. This introduces a degree of unpredictability, ensuring that the universe evolves over time. In this view, our actions may not be entirely free, but they are part of an ever-changing cosmic story. At its core, the Ekpyrotic model invites us to reconsider what we mean by reality. If branes exist in higher dimensions and our universe is merely a product of their interactions, then our perception of the cosmos is inherently limited. We are like shadows on a wall, glimpsing only a fraction of a much larger, more complex reality. This perspective echoes ancient philosophical ideas, such as Plato's allegory of the cave, and invites us to explore the deeper mysteries of existence. As we unravel the mysteries of the Ekpyrotic Universe, one unavoidable question arises: what does this mean for humanity's place in the grand scheme of things? If the universe is an eternal, cyclical entity, how do we fit into this infinite dance of creation, destruction, and rebirth? In the Ekpyrotic framework, our existence may seem like a fleeting moment in an endless cosmic cycle. From the perspective of brane collisions and multidimensional physics, human life could appear almost insignificant, a brief spark in an eternal symphony. Yet, it is precisely this vastness that gives our existence meaning. The universe's cycles, no matter how immense or ancient, have led to this moment, this particular arrangement of atoms, planets, stars, and consciousness. In that sense, we are not insignificant. We are an expression of the cosmos itself, capable of understanding and exploring its mysteries. If the universe is truly cyclic, then every bit of knowledge we uncover today contributes to a larger, timeless tapestry. Even if civilizations rise and fall across cycles, their discoveries and contributions may ripple through the cosmos, influencing future iterations. Could our understanding of the universe be imprinted in some way, carried forward across cycles like echoes of an eternal symphony? This perspective imbues human endeavor with a profound sense of purpose. We may be small, but our quest for knowledge ties us to the very fabric of existence. By exploring theories like the Ekpyrotic model, we become participants in a cosmic story far larger than ourselves. Perhaps the most tantalizing question of all is whether the cycles themselves have an end, or whether there is something beyond them. If the universe is eternal, does it eventually evolve into something entirely different, transcending its cyclic nature? Are the brane collisions we imagine today just one phase in an even greater cosmic narrative? These questions remain unanswered, but they invite us to think beyond the limits of our current understanding. The Ekpyrotic Universe doesn't just redefine the cosmos, it reshapes how we perceive our role within it. The idea of an eternal universe offers a sense of hope and wonder. No matter how vast or ancient the cosmos may be, it is also deeply interconnected, and our existence is a testament to its intricate beauty. Whether through science, philosophy, or exploration, our search for meaning becomes a vital thread in the endless tapestry of reality. The Ekpyrotic Universe is more than just a scientific theory. It's a cosmic story that challenges our understanding of time, space, and existence. By proposing an eternal cycle of creation and destruction, it offers a vision of the cosmos that is both awe-inspiring and humbling. Whether or not the Ekpyrotic model proves to be true, its implications for science, philosophy, and human understanding are profound. It reminds us that the universe is a place of endless mystery, where every discovery opens the door to new questions. Curious about the mysteries of the cosmos? Want to explore the theories shaping our understanding of reality? Hit the subscribe button and join us on this journey through the universe. Don't forget to like this video, share it with fellow space enthusiasts, and let us know your thoughts in the comments below. Together, let's uncover the secrets of existence, one cosmic mystery at a time.